So as we've seen, we can calculate the average rate of a reaction if we choose 2 time points, and then we look at the concentration of the reactant and how they change during that time, and divide it by the time that it takes for it to happen. If we were to calculate the rate over shorter and shorter time periods, in other words, if that time period shrinks and shrinks and shrinks and shrinks and shrinks, what we can actually get is the rate. We can calculate the rate over an instant in time, and that's known as the instantaneous rate of that reaction, right? And in the majority of cases, that instantaneous rate is way more useful to us, especially as chemists and what we're studying, than the average rate of a reaction. So what that is actually equal to is, and we've seen before, if we plot the concentration of, in our reaction, the concentration of bromine over the course of time, you see the concentration of bromine decreases, right? And it decreases not in a linear fashion, it decreases in a curve, sort of like an asymptote. And what the instantaneous rate would represent on that curve is actually a tangent to that curve. And specifically, the instantaneous rate would actually be the slope of that tangent to the curve at any point on the curve. Okay, so you can say, for instance, if we pick a point after 100 seconds, or right about here, so we pick a point, this would be this point, and I draw a tangent to it. Now, a tangent is a line that just touches the curve only at that point. So I can extend this line, this tangent, to infinity in either direction, and I can pick any 2 points along that tangent, and I can determine rise over run, okay, and I can get my the slope that way, and that slope is equal to the instantaneous rate of that reaction. As you can imagine, also, that's instantaneous rate as time passes, and it changes as we progress from one part of the curve to the next. So for instance, the rate of 100 seconds, that instantaneous rate is 2.96 times 10 to the negative 5 molar per second, whereas the rate at 300 seconds is 1.48 times 10 to the negative 5. So the rate has decreased, and as you can imagine, the slope down here is not as steep as the slope here. As a result, the rate is lower. And we know that should be the case because as time passes, the concentration of Br2 decreases, and as the concentration goes down, the reaction rate goes down as well, according to all those reasons we mentioned early on. So as the reaction rate we mentioned decreases, according to this graph that we have here, the reaction rate decreases with time. And the reason why is the concentration of bromine, Br2, a particular reactant in question, in this example, decreases with time as well. So what we can do is we can actually compare different time points, different instantaneous rates along this reaction pathway. So these are instantaneous rates. And from this point onwards, we're going to assume that the rate that we're talking about is going to be an instantaneous rate unless explicitly stated otherwise. All right, so again, for our same reaction that we did previously, we have time equals 0 to begin with. The instantaneous rate at that point is 4.20 times 10 to the negative 5. We have an instantaneous rate at time 50 seconds and an instantaneous rate at time 250 seconds. So if we pick two of these data points, two of these time points, we can make some comparisons. So for instance, if I pick the concentration of bromine after 50 seconds, so this data point here, and I compare it to the concentration of bromine after 250 seconds, right, which is the third year. And if I divide these two, so specifically now I'm looking at the concentration. So if I divide the concentration of bromine, the concentration of Br2 after 50 seconds, I divide that by the concentration of Br2 after 250 seconds. okay, what I end up with is 0.0101 divided by 0.00500. That gives me approximately really close to 2. Okay, so as the concentration, or we speak between the 50 and the 250 seconds, right, the difference there is the concentration of the bromine has actually halved. Well, what happens to the rate at those 2 time points as well? So if I compare the rate after 50 seconds to the rate after 250 seconds, what do I notice? Well, I divide the 3.52, after 50, times 10 to the negative 5. I divide that by the rate 350 seconds, 1.75 times 10 to the negative 5. Guess what? That also gives me approximately equal to 2. So in other words, comparing those same 2 time points, if I have the concentration, if I have the concentration of bromine, I also have the rate of the reaction. So I can make a very, very simple relationship. I can say the rate is directly proportional to the concentration of bromine, right? Because if I do one thing to the bromine, I see the same thing happening to the rate. That's a direct relationship. I can take this proportionality relationship and I can turn it into an equality, which we've done a lot in Gen Chem 1. So I can say now the rate is equal to, so when you replace the proportionality symbol with an equal sign, guess what? You have to introduce now a proportionality constant. And that proportionality constant in this particular instance is called K, or is K, and then this is known as the rate constant for this reaction. And then that's times the concentration of Br2. Right, we saw this at least a couple times back in Gen Chem 1 when we went from a proportionality to an equality. When we change the proportionality to an equality sign, we have to introduce that constant in there. Right, so K is called a rate constant. So we can say the rate is equal to K times the concentration of Br2. We can rearrange this equation very simply, do a little bit of mental gymnastics on this. And we can solve it for the rate constant K, and we can see how K, the rate constant, is going to be equal to, let me do this in a different color. So K will be equal to the rate divided by the concentration of Br2. Okay, so we can solve for the rate constant for this particular equation by picking a couple data points on here and seeing the relationship between them. So let's solve for K, the rate constant. So for example, if I pick, let's pick the time equals 50 seconds, you can pick this one. Okay, so for time equals 50.0 seconds, the rate constant K would be equal to the rate at that time. So 3.52 times 10 to the negative 5 molar per second divided by the concentration of Br2, which is 0.0101 molar. Okay, so molar cancels. We divide those two, stick it in your calculator. What we end up with here is 3.49 times 10 to the negative 3. And then my unit there would be per second. I can do the same thing for the rate constant at time equals, let's say, what else do we have here? 250 seconds. So we can do that one. Well, so for t equals 250 seconds, our K would be equal to the rate at that time, right? It would be 1.5 times 10 to the negative 5 molar per second divided by the concentration of Br2 at that point, which is 0.0500 molar. Molar cancels. Our unit there is also going to be second to the minus 1. Stick that in the calculator. And we get 3.5 times 10 to the negative 3. So what we see here is within rounding errors, right? This is the same as round it to one decimal place, we get the same value, right? So that's important because what we just solved for is a rate, is k, which is the rate constant, right? And constant by definition is something that does not change. So it doesn't matter what the concentration of bromine is, the rate constant is going to be a same or the same value. So what we will see now, and we'll see this later on down the road, okay, the rate constant is a constant. That's sort of obvious, maybe. The rate constant is a constant value, hence its name, and it does not depend on the concentration, in this case, of the reactant Br2. However, and this is important, it does depend on temperature, right? So we can say then the rate constant is a constant at the rate constant is constant, the constant temperature. Okay, so we'll see later on in a couple sections down the road how K, the rate constant, does depend on temperature. But according to the name, it's a constant, doesn't change, doesn't depend on the concentration of the reactant, in this case, of which is Br2.